Welcome to another seminar for structural engineers. This is CPD seminar number 28, primarily for structural engineers. It's aimed at graduates, but anybody involved with structural engineering needs a reminder of some of the basics of structural engineering. Today we're going to be talking about stiff diaphragms and lateral load distribution, and also looking at accidental eccentricity that arises from seismic action. So in this case, we're looking at concrete walls and how we distribute loads within those concrete walls. And these walls are supporting a stiff concrete diaphragm, and it's subject to seismic loads. And these seismic loads will give torsion on plan due to accidental eccentricity. And today we're going to be following the procedures laid out in the New Zealand Standard 1170 Part 5, as well as the New Zealand Society for Earthquake Engineers, a good set of guidelines they give. We'll also be looking briefly at the Redco spreadsheet and wondering all about what that thing does. So a brief overview of the contents. So a reminder of some building components that we'll be looking at, how we derive seismic loads, where diaphragm action comes from, and we'll refer to the New Zealand Standard as how we apply those design actions and how accidental eccentricity comes about. The different types of diaphragm analysis, so I'll remind you later in the seminar of what types of analysis you can do for diaphragms. Brief look at the Redco spreadsheet, and then a deep dive into the Mathcad spreadsheet. And then final words on transfer structures and whether we apply accidental eccentricity to parts of structures. And what about equipment? Do we have to apply accidental eccentricity onto equipment? So here's a nice pretty picture of some building components, and we'll be looking in particular at transferring forces through concrete floors, which are acting as stiff diaphragms. These are then transferred into the shear walls. Now diaphragms can perform a number of functions, as we'll discover later in the seminar, and normally if you're looking at wind, for example, wind on the face, we can distribute the wind on the face to the lateral resisting structures on the side of the building through the diaphragm action of the floor. And here's a reminder of how seismic loads are derived, looking at NZSEE 1170.5, and it's in clause 6.2. We have, well, first of all, we've got seismic weights for each of the floors, and we add it up to get a total. We multiply it by a CDT factor, and that gives us our base shear. So that's the shear at the base of the structure, and that needs to be distributed up the building, and we use these formulas here given in clause 6.2. So we have this exception on the top floor, so that the top floor shear is 8% of the base shear, and then we distribute the rest of the forces in proportion to the stiffnesses and the seismic weight applied at that particular floor given its height, and you end up with something that looks like that if you add it all up. And this is quite an old calc that I've pulled out of the archives, and you get some nice neat calculations to show what the forces are in each of the walls when subject to seismic loads. Now this is for one set of walls on one grid line when subject to a seismic force in one direction. So this is quite happily ignored accidental torsion. On a simple view, the ground moves in a seismic event, and you end up with inertial forces in your structure above the ground, and that is now getting down to the ground through your shear walls. And again, this diagram quite happily ignores accidental eccentricities. But that's the basic principle of it. and referring to the New Zealand standard 1170.5. And if you're doing a simple analysis, an equivalent static analysis, we can apply our loading as 100% in one direction plus 30% in the other direction. And this is for a nominally ductile or a brittle structure. So this is usually low ductility structures you're looking at. However, you've also got to consider accidental eccentricity. So for actions applied in the direction parallel to the principal orthogonal axes of the structure, the eccentricity shall be taken as not less than plus or minus 0.1 times the planned dimension of the structure at right angles to the direction of the loading. So this is quite conservative, because in other standards, in particular the Eurocodes, they use 5%, not 10%, and I believe the American standards use a 5%, not a 10% eccentricity. So this is the diagram from NZSEE, the guidelines, and I've just noticed there are some errors with this diagram. So if anybody can spot them, there's a bonus point if you can explain what the errors are in this diagram. Just answers in the chat, please. But basically, you've got walls in the X direction and you've got walls in the Y direction. For their example, the walls in the X direction are all the same. So what they're saying is that the eccentricity in the Y direction for the walls in the X direction is 0. So this really should be X v Y equals to 0. And we've got this extra wall here, which means we've got an eccentricity of this applied stiffness, and then we apply a difference of 0.1 to it. So diaphragms, we're all familiar with diaphragms. We're usually suspended floors, they're usually relatively thin and they're usually horizontal, and we ask them to do more than just carry vertical loads. We often ask them to carry the lateral loads as well. The diaphragms transfer these internal forces from themselves and to the connected elements and onwards to the lateral force resisting structure. They perform a number of functions as well as resisting gravity loads. They carry the gravity loads, they provide the lateral support to the vertical elements, they complete the framework for lateral forces of resistance, and they transfer lateral inertial forces to vertical elements of the seismic force resisting system. They resist out-of-plane forces, for example wind, as well as seismic loads. They can resist thrust from ramps, stairs and inclined columns if you have such things. And they will control the deformation compatibility through the diaphragm. And finally, if you've got a diaphragm below the ground, they'll be responsible for transferring the hydrostatic and soil loads to the resisting system. There's a number of ways of modelling diaphragms. The simplest, of course, is a beam model, and we'll look at strut and tie models. You can go on to grillage models. But you may need to think about whether your diaphragm is rigid or whether it's flexible, which makes a difference as to how your load is transferred and how your load is shared between the walls underneath. We'll look at end fixities and stiffnesses, as well as defining the center of rigidity or the center of stiffness. And we'll come across inherent and accidental eccentricity. Then we'll go on to describe the distribution of the forces into the shear walls. And here is the beam model. This is a nice diagram from FEMA, and I'm sure you're all familiar with beams. If you've got a lateral load applied on one side of the building, it can be transferred to your shear walls on the sides of your building, like it was a beam, which gives you shear on the ends, and you've got a compression and a tension force in either side of your beam model. NZSEE likes to look at strut and tie models, and it gives you this nice little diagram here about imagining there's struts and ties within your concrete floor, and you can distribute your load simply through that. However, if you've got irregular buildings, your strut and tie models can get a little more complicated, and in some cases the strut and tie models are not applicable, and in other cases they are. And they're recommended for simple analysis, and strut and tie models are usually good enough to be done by hand. However, there comes a point where it becomes difficult to do it by hand, particularly if you've got irregularities in your structure, or holes on plan, for example. So if you've got significant asymmetry in your lateral force-resisting elements, then you may require a more sophisticated analysis. And this is where you get things like grillage models. And here is an example again taken from the NZSEE Guidelines. And I wouldn't try to do this by hand. Shove this in a finite element modeling package, for example, something like ETABS. And grillage models can get very, very complicated. So how do you know whether your diaphragm is rigid or flexible? Now, this isn't written in the code, in the New Zealand code at any rate, but if you delve deep enough through the references, you'll find reference to the American codes, and within that you'll find this diagram of a diaphragm. So it's about relative stiffness. So here is the deflection of your diaphragm due to flexural action. And here is the deflection of your supporting structure through sway. So if this dimension here, the deflection due to the diaphragm flexural deflection, is more than twice the sway deviation, then your diaphragm is probably flexible. Otherwise, your diaphragm is rigid. Now, as a rule of thumb, if it's concrete, it's probably rigid, and if it's timber, it's probably flexible. But there are extreme examples of either, because you can have rigid timber diaphragms and you can also have flexible concrete ones, and it's about the relative stiffness between the diaphragm and the supporting structure, whether it's walls or columns. So how do we work out the stiffness for each of the walls? Well, the stiffness is basically the inversion of the deflection, and the deflection is made of the sum of the bending deflection and the shear deflection. So the shear deflection is relatively simple. It's a 1.2 multiplied by the applied lateral load multiplied by the height, and we divide that by the shear modulus multiplied by the area of the wall. Flexural deflection, well, it depends on your end fixity. So if you've got a fully fixed wall, that's fixed top and bottom, you're dividing it by 12 times the elastic flexural modulus multiplied by the second moment of area for the wall on plan. And if we have a cantilever wall, I basically fixed only at the bottom, then the denominator is 3 rather than 12. So you can have an arrangement which has got a mixture of shear walls. Some will be stiffer than others depending on their end fixities. Here is an example for a wall layout. So we have X in this direction and Y going up the page. So our length in the X direction is going to be BD, and our length in the Y direction is going to be LD, and we'll use those figures in the calculations to come. So we have a number of walls in the X direction, and we have a number of walls in the Y direction, and immediately you can tell that this is not going to be a concentric resistance system. So there is going to be a natural inherent eccentricity of our resisting system because of the layout of the walls. So we'll assume that the center of mass, where the load is applied, is going to be in the middle of this nice rectangular floor. But our center of resistance, or a center of rigidity, or a center of stiffness is going to be offset, and we're going to use the values EX and EY for the offsets in the X and Y direction respectively. And so we have inherent eccentricity, as you can see here, but then because of the code, they're saying let's have some accidental eccentricity, and we add 10% plus or minus. So you end up, in effect, with 4 load cases, 1 plus eccentricity, 1 minus eccentricity in each direction. So here are the distribution of forces. So for walls in the X direction, you simply take the shears and divide it by the shear for that resistance for that wall divided by the total multiplied by the applied load. Similarly, on the right-hand side, we've got the torsional moment, and this is what you're looking at is the torsional rigidity of the system. And so we have the torsional rigidity for the particular wall divided by the torsional rigidity for the whole system, and then you multiply that by the applied moment. And so we have 2 eccentricities in the X direction and 2 eccentricities in the Y direction. The shear forces in the arising, quite simple. You put them and divide them in proportion to their stiffness. However, because of our eccentricity, we're having a torsion on plan. And this gives rise to moments and gives rise to shears in the walls around the building. Similarly, let's go through in the X direction. You apply your load in the X direction, and the shears in the shear walls in the X direction are simply transferred in proportion to their stiffness. However, because of the eccentricity, we've got this moment on plan, and that is distributed to the walls all the way around in proportion to their stiffness and distances from the center of rigidity. You'll notice that this torsion on plan gives rise to forces in the Y direction, not just in the X direction. Here is our Redco spreadsheet, and what a marvelous thing it is. And you do so many things in this spreadsheet, and I think you do far too many things in this spreadsheet. Not only are you distributing the loads, you're designing the walls. And I'm sure you all use it with confidence because you know what you're doing. However, for those who are just using it blindly, let's go into a lot more detail. And a lot more detail is going into Mathcad. So let's open the Mathcad. Okay, so I'm going to do it twice, once for the engineers and once for the Mathcad geeks. So here is the Mathcad for the distribution of seismic loads via a stiff diaphragm into our concrete shear walls. So we set out the diaphragm dimensions, so width and lengths, 20 meters and 10 meters, and we have our story height set as 3 meters. We apply our seismic force in one direction, so in the X direction it's 100 kilonewtons, and then we can take 30% of that and apply that in the Y direction. We'll assume for simplicity that the application of the load is in the center of the floor, which is assumed to be where the center of the mass is. We put in some properties for the concrete grade, and the modulus of elasticity is 25 GPa, and the modulus of rigidity as 10.4 GPa, which we're now deriving from the modulus of elasticity. We put in our strength reduction factors as required, and then we move on. So here is the wall layout we showed before, and then we've got 2 exercises, one in the Y direction and one in the X direction. So we enter the coordinates for the positions of the walls and the length of the walls in the X direction. So the first wall is 6 meters long, it's 200 millimeters thick, and it's 100 millimeters off the X axis. And we're telling us here that it's basically a cantilever wall. It's got a moment out the base. The next wall has got moment top and bottom, and the third wall is a simple shear wall. So we then work out the wall properties from that. So we've got the lengths of the walls, so 3 and 4, the areas of the walls, the second moment of area for the walls, and then we have the stiffnesses derived for each of the walls depending on whether it's a shear wall, whether it's a cantilever wall, or whether it's a fixed wall, top and bottom. And we repeat the exercise in the other direction. Moving on. We then calculate the wall stiffnesses and the total wall stiffnesses in each of the directions. Here's the y direction, and then we have walls in the x direction for wall stiffnesses and total wall stiffness in the x direction. From that we can derive our center of rigidity by summing the stiffnesses and eccentricities and divide it by the total stiffness. So that gives you the resultant x offset, and similarly a y offset for the walls in the x direction. So then we derive the wall offsets from the center of rigidity as Rx, and so we have 4, -4, 3.5 and 15 for the walls in the y direction. And this is shown in this diagram here. Then we can tot up the eccentricities and apply the accidental eccentricities. So here is our inherent eccentricity, but here we're adding our accidental eccentricity as 10% of the dimension in that direction. Then we look at the rotational stiffnesses of the wall systems. So for each wall in turn, we work out what the torsional stiffness of the wall is, add up the grand total, and then there's the sum of the squares to give us the total for the system. And we do it in the y direction and then do it in the x direction and tot up the total together. So that is the total torsional resistance of the whole wall system. Now we look at distributing the forces, and so as we can see, the distribution of shear forces is relatively simple. We take the stiffness of the particular wall divided by the total and multiply it by the applied load in that direction. So we do that for the y direction, and here we're doing it for the x direction. And we do a check. Is the total applied shears equal to the applied loads? And here we've got Hy is equal to 30, which is equivalent to the applied load in the y direction. Similarly, in the x direction, the total of the shears is equal to 100, which is the applied load in the x direction. Now we look at torsional moments, and they work out for the 2 eccentricities and the 2 directions. How do we distribute those? Well, we look first of all in the y direction and use that formula that we showed above to distribute the horizontal shear. So we end up with a number of different load cases. So first of all, we'll look at load case 1, which is the force in the y direction with positive eccentricity, and distribute using this formula here. So it's the rotational stiffness for the individual wall divided by the whole total multiplied by the moment. Then we've got load case 2, force in the x direction with negative eccentricity. So those are those 2 load cases here, and that's where we've distributed the load applied in the y direction around the shear walls. Then we've got load case 3, which is a force in the x direction with positive eccentricity. And then we have load case 4, which is a force in the x direction with negative eccentricity. So there's 4 potential load cases there, and this is only looking at the force originally in the x direction with a complementary force in the y direction. There's 30% of that applied in the x direction. And so we then summarize the forces and get the grand totals of the total force in the walls in the y direction and the walls in the x direction. And that's it, nice and simple. I said I'd do it again, and I will do it again. So I'm going to show my working out and for the benefit of the Mathcad geeks. So we go back to the beginning, and let's make it a little bit bigger. So we put in our dimensions as we've shown. There's our wall layout. There's the basic properties for the walls, so the wall areas, the second moment of area, the wall stiffnesses for shear and torsion. So I've hidden something in here. How do we get the total wall stiffnesses? Well, because these are arrays, we need to create a matrix. And we create a matrix in each direction. So we start by defining how big our matrix is, and that's dependent on the length, the number of walls. So in this case, we've got 3 walls, and we start with initial value of 0 for the shear, and we populate this matrix. So in the 0 column, we have a number. The column marked 1, we have the length. Column marked 2, we have the thickness. Column marked 3, we have the area. Column marked 4, we have the x dimension. For 5, we allocate the stiffness, and we do an if. So if it's a fixed wall, we have this kind of stiffness. If it's a cantilever wall, we have a second type of stiffness. Otherwise, it's a plain shear wall. And then allocate that to the 5th column, and in the 6th column, we multiply that by the eccentricity from the x direction. So we repeat that exercise on the right-hand side. Similarly, walls in the x direction for wall stiffnesses. There is our table that we've just derived. And from that, we can pull out our wall stiffnesses is the 5th column in our matrix. And because our matrices are indexed from the number 0, we have the column here to populate the wall stiffness. And the wall stiffness multiplied by the x value is the 6th column. And we do the same for walls in the x direction, and then creating the sum total to create the final tables. So again, we're creating a matrix from the whole set of arrays we've already had and populating the tables. So here is the basic shear, and these are the 4 load cases, and then we're doing a comparison with the maximum of the loads in either direction to get our final figure, the HY. Okay, so that was the Mathcad. Transfer structures, well, try to avoid them if you can. But if you have transfer structures, it makes your load distribution a lot more complicated, because you're not just transferring loads from your floor, you're transferring the loads that are applied to the floor from the levels above. And you're also transferring those in the proportions to the stiffnesses of the shear walls in the load below. And you've also got the case on the right-hand side where your stiffness is significantly smaller. So your distribution of the forces on this level, the lower level, is going to be different from the distribution of the forces from the upper level. What about parts? Accidental eccentricity does apply when you're using seismic actions on parts of structures. So this is section 8 of 1170, part 5. And it's not just applying to suspended ceilings. And in some cases, we design the upper structure. If it's a steel frame as the top story of a concrete frame building, you'll often design the top story using parts, because the behavior of that top story will be different from the behavior of the lower stories. And So, yeah, accidental eccentricity is typically accounted for by applying a torsional moment based on the seismic lateral force and the specified diaphragm eccentricity. But it is worth thinking about. If you've got big heavy loads that need to be held up on the top of a building, it's not just the seismic load due to parts, it's also the eccentricity due to the application of that seismic load. Similarly with piping networks, you can have eccentricity due to seismic loads on that. Obviously you can accommodate movement by putting in seismic restraints as well as flexible joints. Storage racks, yeah, they can be eccentrically loaded, and you need to account for that with an additional potential torsion on plan on the legs of those storage racks, and therefore your anchors to the floor need to take that into account. Elevator systems, yep, they could be subject to accidental eccentricity. Suspended ceilings, now this is one the council gets quite excited about. So suspended ceilings will nearly always be designed as parts, and normally, certainly for most commercial buildings, the ceiling is relatively light and the seismic load arising from the suspended ceiling is relatively small, but it still needs to be restrained, and we don't want it to fail in an earthquake. This is doubly so when you're loading up the ceiling with bits of equipment as well. So obviously the ceiling, if it's suspended, needs to be restrained. Heavy machinery, as mentioned before, whether it's on the ground floor or whether it's on the top floor makes a big difference, but in both cases you will still need to design the supports for your heavy machinery to take into account the movement during a seismic event and potentially accidental eccentricity. But I'm guessing this will be covered in equipment regulations rather than structural regulations. The bit that we're interested in is how that machinery transfers its load to the structure. And we've often assumed that it's applying it uniformly at each of the legs. This may not be the correct approach. Yeah, recommend you use base isolators to reduce the transmission of those forces to the rest of the building. So that was the main seminar for seismic distribution of forces in shear walls, concrete shear walls through our concrete diaphragms. Our next seminar is on retaining walls in about a month's time.